So welcome to Google, Google in Cambridge here. Today it's my pleasure to introduce Paul Horowitz, professor at Harvard, down the road from us. I knew Paul Horowitz when I was in college back then. Many of you know him as the author or the co-author of a book called Horowitz and Hill, The Art of Electronics, which is a fantastic textbook and reference for people who are both electronics hacker professionals and electronic hacker amateurs. Paul has a third edition of the book just out, and I contacted him and I said, come talk to us and come give us a book talk. You can come read from the chapter on field effect transistors, entertain us. And I thought that would be great. But he said, you know, he's got this day job. His day job is looking for extraterrestrials. And that turns out to be interesting as well. So I said, sure, come talk to us about that. So he'll do that. I think he'll be taking some questions at the end. We can talk about the book a little bit then as well. But I imagine this will all be great fun. So without further ado, Paul Horowitz.
So I'm going to talk generally about the subject of SETI, and specifically about some of the stuff we've been doing at Harvard. And I'll tell you also about some of the new stuff going on. You may have heard that $100 million got given in a thing called the Breakthrough Listen Initiative by the Breakthrough Foundation, Yuri Milner. And that thing's just starting up now. OK, so, but it's really nice to see David after 25 years. I should just tell you about David. When he took our electronics course, he did, as he's described here, he's a zealot to show what he could do with our little computer that you build. This is the circuit of it, in case you'd like to see. From the bare metal, we had the students build this thing, really wire by wire. And it's really, really bare metal. You may notice some things that are missing. For instance, there's no keyboard, there's no monitor, there's no disk, there's no operating system, there's not even a serial port. And David managed to outfit this thing with a set of DACs and extra memory, and he did bit banging to make a serial port, and he programmed this thing to play asteroids. So we thought that was pretty spectacular, and he earned this little notice in our student manual. So that was pretty cool. I'm not surprised to see him at the Googleplex. He's that kind of guy. I remember he needed a quad DAC for this thing, and he got on his bike and bicycled out to Analog Devices to get the part to make this thing. So pretty cool. All right, I'm going to try here to put an awful lot of stuff in here, and since I'm not really quite sure what backgrounds are out here today, I'm going to try not to be boring, throw a little bit in for everything. I'm going to start with a slide after this one. There was a series of talks at the MIT Museum a few years back called, what was it called? Life in the Universe. And the last talk was on finding them. And the one before that, I went to just to see what kind of people go to these things. And one of the questions during that session was something like this. I've heard that spy satellites can read license plates down on Earth here. Can't we just do that on planets around other stars? And the guy who was talking said, well, I think that's a question for next time. Well, next time was my time, so I decided I'd start with a slide. So here's the slide, which is, well, what about the license plate myth, and what about other planets? So here's the deal. You can just do a basic optical calculation, which is look at diffraction-limited resolution, looking down, turn the Hubble in the wrong direction, programming error. You're probably running Windows or something. And if you take the actual parameters of Hubble, fly it a little low, about 100 miles, and just look at what the diffraction-limited resolution is, about 1.6 inches. So you could read large license plates. Of course, license plates are on the backside of cars, so if you're looking straight down, you wouldn't see it. You have to put a license plate on the top. But anyway, the number's about right. But then what about doing this on other planets? Well, let's go for some serious distance here. Let's try a planet around a star about 25 light years away. That's far enough out to have some reasonable number of candidates for habitable planets. And the good news is that there's no problem with the brightness. You might think, well, far away, you don't have very many photons. But that's not the problem, because you have to use a bigger telescope to get the same diffraction-limited resolution, and that's going to scale up like the distance. So when you scale up the telescope proportional to the distance, then the resolution to keep the same resolution, then the collecting area goes up the square of the distance, and that exactly compensates for the fall-off of light, which is square of distance. So you got plenty of photons, no prob. The prob is you need a kind of big telescope, and here's how big it is. It works out to be about 18 AU. An AU is the mean distance of Earth from Sun. And so I made a little scale model here. There's an antenna it's about the size of Saturn's orbit. Kind of big, and people don't make optical telescopes that big, so I just stole a radio telescope picture here. But the other thing is it has to be kind of accurate because this is light. It has to be diffraction limited, so it has to be accurate to better than 20th of a wavelength of light. Works out to be about 1,000th the diameter of a human hair. This is an interesting antenna. But then you think, okay, if they have license plates, then they have cars and they have laws, and that means they have police, and that means they have police radios, so they know about radios, so they know about radio communication. Why don't we just ask them what the license plates look like instead of doing this kind of crazy thing? So that gets you into the whole business of communication over these distances. So here's a nerdy slide. Some of these slides are sort of warning away nerds, but you guys are nerds. There's no problem here. So here's the question: can you communicate over these distances? And you might start with. By the way, I'm not a PowerPoint guy. Maybe you can tell. But I did learn about the animation, but all I could figure was you could fly in from the left. So a lot of stuff flies in from the left. Sorry about that. So take a couple of modest-sized dishes, 300 meters. That's the size of the Arecibo Great Dish down in Puerto Rico. Put these things a modest distance apart, like 1,000 light years. Within 1,000 light years, there are about 1 million sun-like stars. So this is a reasonable piece of the galaxy. It's about the thickness of the galaxy out where we live. And transmit $1 worth of electrical energy converted into radio waves. So here's the thing called a nerd box. And the nerd box simply calculates how much energy will be received if you transmit $1 worth with diffraction-limited antennas of this size. And it works out to be about 2 times 10 to the minus 11 ergs when you scratch through the thing. By the way, the antenna has quite a lot of gain there. I just marked in there. It's about 90 dB of gain, factor of 10 to the 9th. So that helps a lot. Big antennas, short wavelength, that's good. But what's 10 to the minus 11 ergs? What does it compete with? Well, it competes with background. Oh yeah, you got to have the little thing here, again for the regular audience, which is when you get to the punchline, that's the good part. This is one of those Sid Harris cartoons used without permission here. This works out to be about 1/trillionth the energy of a falling snowflake. So it's not a lot of energy there, but it competes with even smaller background numbers, which is thermal noise. And at these kinds of wavelengths, you can achieve system temperatures of 25 kelvins or even less, or about 10 to the minus 15 ergs, a few times 10 to the minus 15. So in other words, the received signal is about 10,000 times noise. No prob. In fact, you could chop it up in little bits and send a whole bunch of bytes. So interstellar telegrams are cheap. This is, here's again the same diagram. And they cost something like half a cent per word. This is a calculation originally that I saw from a wonderful professor at Harvard by the name of Ed Purcell. Perhaps some of you know his E&M book. Anyway, that sounds good. What's coming next? I guess what's coming next is, okay, but what's out there within 1,000 light years? And here's a little picture of the galaxy. It's kind of a flat thing with lots of stars. Some are red, some are blue. There we are out in the, does this pointer work? Oh, this pointer works, yeah. Can you see that? Ah, all right, here we are, sort of in the galactic suburbs. And in the immediate region where we are, the galaxy is about 1,000 light years in thickness where most of the stars are in the disk. And there's about 1 million like the sun, the number I made before. So there's plenty of candidates. And as we know from recent exoplanet searches, experiments, things like Kepler and so on, most stars have planets, and probably 20% of them have Earth-like planets, inhabitable. Maybe 10 or 20% habitable Earth-like planets. That's an amazing number. That was not 20 years ago. Nobody knew that. In fact, nobody had any examples of planetary systems anywhere except here, and one weirdo with pulsars. What's this say? Oh yeah, and if you're worried that that's not enough stars, I don't know why you'd worry. There's 10 to the 11th galaxies. The only problem is there's that pesky speed of light thing. So they may be out there, but it's kind of annoyingly long round-trip latency. All right, if you want one of these gee-whiz numbers, here's a gee-whiz number. There are more stars in the universe than grains of sand on all beaches of Earth. And I can say this with some authority, having done a back-of-the-envelope calculation, which just flew in from the left. And what I did was I was generous with my beaches. I let there be 100,000 kilometers of beaches. You know, the Earth is kind of, beaches, shorelines are fractal kind of, and they zigzag in and out. I gave these things 100 meters of depth. You know, that's a pretty good beach, and out toward the water, 30 feet deep, not bad, huh? So there's 10 to the 11th cubic meters of beach, and I gave sand a 0.5 millimeter cube. That's about 10 to minus 10 cubic meters, so you get 10 to the 21 grains of sand. But there's 10 to the 22 stars, at least, in the universe. So there you go. I showed this thing. This is done on the back of a Crane's beautiful envelope, and I showed this thing at a conference called EG in California. A whole bunch of very interesting people go to that, and one of them is the Mythbuster guy, the guy with the red hair. What's his name? Adam Savage. And he said afterward, he was at this thing. He said, I got to have that envelope. He said, send it to me. I'll send you something really cool. So I mailed the actual envelope. This is all I have left, and he never sent me anything. So, Savage, right? Okay. So planets. How do you find planets? Well, people have been finding planets like crazy in the last decade. One way to do it, the first way that really worked, was spectroscopic. You look at the spectral lines of a star, and the recoil planet going around gives you a Doppler shift, periodic Doppler shift. It's not so easy to do. You know, there's turbulence on the star. You have to do this very precisely. They throw an iodine absorption cell in there to give calibrated lines to sort of compensate for everything that goes wrong. And then you look at the Doppler shift over time. Here's an example of a pretty heavy planet in a pretty slow orbit around another star. You see this one, they've been going on for about 10 or 12 years. You see about one full cycle. So this is the radial velocity method. It has a strong bias toward heavy close-in planets. Close-in because it goes rapidly and you get to see several cycles. Heavy because you get a big recoil velocity. Actually, the close-in also gives you more velocity. So it tends to favor heavy close-in, that is hot Jupiters. And the very first planet found was a Jupiter in a several-day orbit. Completely unexpected. We don't have those things here. And so people started to wonder, do we live in the weird planetary system? And in fact, the whole universe out there is hot Jupiters. But no, it's really a selection effect. And when you do more careful measurements and try to dig down into the harder to detect planets, you actually find that Earth-like planets are rather common. Now, I have a little bit of stuff on this. Let's see. Here's a graph that was put together actually by a former student of mine in SETI. And he's become a big stick in the business of exo-Earth. And looking at a bunch of stuff, this was through radial velocity measurements, the spectroscopic things I just showed. The fact is that, and what he's plotting here is mass here, or minimum mass, because it depends on, all you can see is what if the thing is inclined, then you only get the fraction of, you get the trigonometric projection of the thing. But here would be an Earth mass down here. And what you see with this part here that's all blue is basically the search is incomplete down there. In fact, it's 0% complete because it's really hard to see slow light planets. But you can take what you have here and extrapolate based on the incompleteness. And from that, you can get a measure of what's down there. And from extrapolation, which is admittedly a bit hazardous, you get something like a quarter of sun-like stars harbor a close-in planet of Earth-like mass. More recently, this other technique, which is of transits. So a planet goes in front of a star, and if we happen to be in the plane of the orbit, then we're going to see a little dimming of the star. Not much. Look at the scale on the left there. So we're seeing 5 parts in 10,000, and that's a pretty big one. And you get this periodic. This is a star with a period of, I don't know, it looks like 40 days there, Kepler 10. Let's see, what have I got here? And based on this kind of stuff, Kepler data, we can try to back out this bias. So here's the orbital period. And again, we favor short ones. And here's radius or mass, 2 graphs here. And again, we favor a lot of mass. So it's complete out here in these regions, right? But down in this corner here, that's the hard place to be. And this is where we live. We live right here, one radius and 365.25 days, except we make a correction every 4 years. No, that's the 4 days. We make a correction every 100 years. Or 300s out of 400. Do you know about that stuff? Most people don't live long enough to care about it. Astronomers worry about it because we got to keep track going all the way back. Anyway, this is the impossible place to go, but we can try to extrapolate and see what you can do with this. And people have done that. When you look, the ones that are hardest to see, you know, we've tried hard. And here's 4 examples. This is from Astrophysical Journal, 2012. This is again my student here. He's really into it. You know, SETI is not a dead end. you learn lots of cool stuff, and you can do other things with it. Here's 4 Earth-like, close to Earth-like planets. These things have a radius of between 2 and 3 times Earth's radius. And this is the kind of dimming you get. And you see, again, we're pretty small numbers here. These are fractional percent dips here. So that's another way to do this thing. Now, wait, it says here, I got another slide in here. It must be here somewhere. Let's see. Got it down. Oh, I guess I exceeded. Anyway, here's a picture based on the Kepler stuff, the transits of what we found as of a few years ago. And here's where we want to be. And again, it's a hard extrapolation, but the best people have been able to do, backing out the selection effects, is that there's plenty of Earths out there. Here's one more graph. Again, with that same incompleteness. Here it's orbital period versus radius again. And again, Earth would be out here, about where my arrow is right there, 365. So Earth-like planets are common. Again, doing the extrapolation, 10%, maybe 20%, depending upon how you do this. And we will know more when we have more data and when we have new missions like TESS and some other things going up. So there's all reason to believe that there's plenty of planets out there. And let me switch gears now and just talk about a different parameter than space, which is time. You know, you might ask, have there been time for them to evolve? You know, are they as smart as we are? Are they as smart as people at Google? What? So let me just show you my little timeline thing. Astronomers love to do this kind of stuff, give you the astronomical perspective, which is everything you know, everyone you know is the thinnest slice of time possible. I think for you guys this is kind of obvious, but anyway, here we are, Big Bang, Earth, Sun, the whole solar system formed about 4.5 billion years ago. And what we do is expand that to one day. So if we call that one day, we can talk about when events happened in this day. The day started when the Sun and Earth were born, approximately. So life arises early on Earth. Look at that, 5 in the morning. Sun wasn't even up yet. Well, that's a bit of a mixed metaphor. But life didn't get interesting until, you know, a few hours before midnight. So now we'll expand that last hour. Here we are, the last hour. Dinosaurs went extinct about 20 minutes before midnight. That's 65 million years ago. So where's the action? Well, the action's really in the last minute. The last minute. Let's see. A minute is, well, it's 50,000 years per second. So you can figure this out. It's a few million years. Here's the last minute. Here's Neanderthals. That was about 100,000 years ago. Maybe things were happening here, but not very interesting. Certainly not for Google kind of interest. So let's take the last second. So a second is 50,000 years. Now things are starting to happen. 10,000 years ago, agriculture. And recorded history basically 5,000 years ago. But look at it. It's a tenth of a second before midnight. You know, does that give you an interesting idea of the compression of time? Or expansion of time, or whatever. Anyway, let's take the last tenth of a second. Now things are happening, right? Here's Jesus, and here's Columbus, and here's the American Revolution, but it started getting squeezed in here. Marconi was 2 milliseconds before midnight. And lasers and radio telescopes and all the stuff that we think you need to communicate is 1 millisecond before midnight. I don't have any more milliseconds, but 20 microseconds is a Moore's law factor of 2 doubling on this scale. And you know, our timeline for technical people is, you know, 1 or 2 years, everything changes. You know, how's your 10-year-old laptop doing? You know? So here's, what's the takeaway, besides this is totally cool? I think the takeaway is if we find anybody out there and they're going to if they can communicate at all, they're going to be in this little millisecond, just barely, but they can be anywhere to the right where the question mark here is. In other words, anybody we communicate with is either, anyone out there is either incredibly dumb or they're so advanced that they're going to blow us away. And so, in fact, if you ask what should we be looking for civilizations that can really do pretty amazing stuff, that can do magic with communications and know all about it. And when if they're interested in communicating with us, it's not going to be to learn about Maxwell's equations or how you make cool gallium arsenide stuff or how you take over the whole world with Google and Amazon. It's going to be about what's your culture like? What wars are you fighting this year? Who's your favorite? You know, tell me about Bach and Picasso and that kind of stuff. Beatles, huh? So that's sort of an interesting perspective. Okay, let's see. What do I got here? Radio works. Anything else? So I showed you before that radio is pretty efficient. And just to set the stage for some of the searches we've done, so is optical. And this was something recognized by Charlie Towns, just a year after the invention of the laser, when he wrote a little paper about communication. So a state-of-the-art laser is really a bright thing, and it's coherent. So if you use a large mirror to make a collimated beam and shine that out somewhere, then someone in that line of sight, and let's assume they cannot distinguish our planet, where we're transmitting this from our star, will see the starlight, but during the time of the laser flash, the star will appear to get much brighter. In fact, about a factor of 10,000. Here's the nerd box. Well, let's see. Here's some laser thing. Here's a little wimpy helium neon laser of ancient times. But here's sort of something a little fancier. This is a NIF type laser that's meant to put out a petawatt. People know how to design these things. They even know how to build them. And here's a graph of laser power through the ages, where the ages begin in the 70s here. Again, that's only milliseconds, right, on the time, not even a millisecond on the time scales that anyone cares about. Here's the most powerful lasers over time. And then it started shooting up here after 1990. Here's this petawatt laser that was actually realized in 1996 at Livermore. This little dashed line here, just for interest, by the way, this is a super Moore's law, huh? We go 2 orders of magnitude in just a few years. What's this dashed line? This is the world's total electric power production. And I know this graph, see, this is the California energy crisis. Do you remember that thing? When Enron sort of took them down. And I drew this graph based on a data point from here and a data point from here, and, straight line. It's the easiest approximation. Anyway, these are powerful pulses. It's only a few nanoseconds, but what the heck? So here's the nerd box. We take one of these diode pump solid-state lasers. It's an ytterbium-doped strontium fluoroapatite. If you're into that stuff. I'm not. And imagine they're doing the transmitting. Remember, they're smarter than us, right? We're not going to do the hard work. We're just going to look for this. So here they are. And they shine it out with a Keck-type telescope. And they send this diffraction-limited beam. And here we look with our Keck. And assuming they only have 10-meter telescopes is really a very conservative assumption. These guys are good. Anyway, here's what you get. You get lots of equations. You count photons. You fiddle around. You even throw in some reality here, like extinction. And get the pi squared over 16 right. There might be someone out there who actually cares about that. And it turns out what you get at 1,000 light years, you get about 1,000 photons per pulse, per 3 nanosecond pulse. And the stellar background, you say, what about the star? Isn't that putting out light? Sure, but in a nanosecond doesn't do much. It puts out 3 times 10 to the minus 2 photons per nanosecond. So you get about 1/10 of a photon from the star, and you get 1,000 photons from the laser. So 10,000 to 1, not bad. And by the way, this is independent of distance, right? Inverse square, inverse square. You can't beat that. So lasers are OK. Lasers are OK. OK, so let me tell you about some searches. Oh, a little silly slide here. What other wavelengths? Well, if you want to do it from the ground, you've got to get through the atmosphere. And that pretty much limits you to the atmospheric windows. How am I doing for time here? Well, we'll just speed up here a little bit. This is going too slow, right? OK. There's the radio window and the optical window. This is actually a nice drawing done by Ed Purcell. Again, this wonderful guy from Harvard. And astronomers exploit these things with telescopes. This is the optical window. So do humans. That's why we have eyes. If the atmosphere were opaque in the visible, it would be kind of silly to have eyes. Nature understood that. In the radio, we build radio telescopes. And here's our little one at Harvard. It actually looks bigger than Arecibo. This is Arecibo. This is 1,000 feet. This is 84 foot. This is my son. Can you see him down there? He's about 6 pixels high. He was 6 years high, 6 years old. He's a year per pixel. And you might ask the question, what about the analog of the eye? Why don't humans have antennas? I don't know. I wonder if there's other creatures that can. That could be really helpful, in a dense fog, or I don't know, in the woods where you don't have direct line of sight. Anyway, and remember, these are very efficient communications. The trillionth the energy of a snowflake gets good communication over these distances. So here's the first detection of radio waves from space. This is Jansky in 1931. He was working for the Bell system. Bell system in those days owned the telephone networks. You may not remember back that far. When I was a kid, you had your dial phone. It was owned by the Bell system. And you couldn't plug your own phone in if you could even find one. They owned it. I took one apart. But I had to put it back together because it was the only phone we had. And there was. Anyway, and Bell System was also doing transatlantic communications, and they were getting static, and they wanted to find out what's the origin of the static. Of course, a lot of it was thunderstorms. But there was this irreducible hiss in the background that Jansky noticed, and being a smart guy, he didn't neglect. that's how penicillin was found, right? It was a rotten cantaloupe in a marketplace. Turned out to be pretty cool stuff. Not the cantaloupe, but the fact that some of the mold wasn't growing in a certain place around the cantaloupe, and there was a little penicillin there instead. Anyway, he noticed that this stuff was coming every day from this. When he pointed to this thing, it was diurnal, 24 hours. But then when he looked more carefully, he thought maybe it was the sun. It wasn't 24 hours, 23 hours and 56 minutes. So you think a day is 24 hours, don't you? Except, wait, I'm at Google. You know a day is not 24 hours, don't you? You know how long it takes the Earth to rotate once on its axis? 23 hours and 56 minutes. You're fooled by the fact that we're going around the sun, and you think the sun is in the same place every day. But of course it's not. We're going around it. So anyway, sidereal time. He figured that one out. He's a smart guy. This was continuum radio waves from space. This is basically the birth of radio astronomy. Here's a little later a birth of spectral line radio astronomy. This is the fourth floor of Lyman Lab at Harvard. And this is Harold Ewan, with his horn antenna, looking for emission from neutral hydrogen. This is 1951. This is what antennas look like then, sort of a hacked-together piece of stuff. Look, little patches stuck in there. So this is basically plywood with copper sheeting stick on there. This thing here is actually a thing that you flip over to cover the aperture. And the reason that Doc Ewan put that there is that he didn't used to have that. And then in a rainstorm, it filled up the lab with water, which he referred to as his first signal from space. So he put that thing in. Here's what it looked like on the other side of the wall coming in here. So here's the waveguide coming in, and it goes to a whole rack of really fancy-looking equipment. This is radio astronomy, 1951 style. Leftover war surplus local oscillators. And look, it's even got earphones so that Jodie Foster can listen for the signal. Anyway, these guys, with a $500 grant, they did this experiment, and they found the 21-centimeter line from hydrogen and founded the whole spectral line thing. Here's 9 years later, Harvard put up the 60-foot radio telescope. This is Purcell and Ewan, and here's the horn that had made the 1951 discovery. And here's that same radio telescope pedestal with a larger dish on it, now 84 foot. Again, with my son there, is 1983. So we pressed this thing into service, and I guess I should say about 1960. This is about the time that people first started looking seriously for microwave signals from space. And here's a shot of Frank Drake's 84 foot, coincidentally the same size as our dish. And here's Frank, back then graduate student, and looked at two stars for a month or two with a one-channel radio. It says down here at the bottom, we turned the telescope to Epsilon Eridani, and then it happened, wham! And as Frank likes to say, all of a sudden, out of the loudspeaker came choo, 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 choo. And they said, can it be this easy? It turns out not to be this easy. It was a satellite. Wait, could it be a satellite in 1960? It was something that went choo, choo, choo. It was probably radar. Anyway, here's Frank a little later at our telescope, a little older then, when we were looking for radio signals. Let me tell you, one more thing about Frank. He's a cool guy. He visited Harvard, and we name our servers, that thing's a server, after SETI people. So this one's called Frank. So we said, Frank, will you autograph Frank? He said, sure. So this is the Drake equation. You guys know about that? How many people heard of the Drake equation? Yeah, okay, good. There it is. And Frank's trying to think, what comes next? And there he goes, Frank Drake. He's quite amused. He's never been asked to sign a server before. Okay. So we started looking for these spectral lines from aliens, and we wanted more than a one-channel receiver, which is what he used for his search in 1960. And what we needed was a Fourier transform type technique. So here's just a little bit of nerd history on the Fourier transform, the fast Fourier transform, which you guys all take for granted. It wasn't always forever. In fact, it was rediscovered in the 60s. And here's a little piece of the story. Dick Garwin, who was at IBM, was the midwife between Cooley and Tukey. And he describes this thing. And Cooley, Garwin mentioned to Tukey that he was computing Fourier transforms and asked Tukey if he had a faster way of doing it. Tukey did. He described the essence of the FFT. Garwin came to the computing center to get it programmed. And as Cooley puts it, I'll read it for you because I probably read it fast. You read. I was new at the computing center. Was doing some of my own research. Since I was the only one with nothing important to do, they gave me this problem to work on. It looked interesting, but I thought that what I was doing was more important. However, with a little prodding from Garwin, I got a program out in my spare time and gave it to him. It was his problem, and I thought I'd hear no more about it and went back to doing some real work. The significance of the factor n log n versus n squared was lost on me since I had never had any use for Fourier transforms. And okay, experience since then has given me quite an education. And when I realized what had happened, I told Garwin that if he had any more ideas like that, I would be glad to help him out again. So it's a wonderful little thing. And Garwin describes, I'll send this thing off to David, and he can forward it around. But basically what happened was that Garwin was sitting at a boring meeting, and he noticed Tukey doing, as he says, doing Fourier transforms with his left hand. He doesn't say whether Tukey was right-handed, but I think that must be the implication, that this guy was so cool he could do Fourier transforms with one hand. Well, anyway, he asked, was there anything you knew about it? He said, yes, indeed, and there it was. And that's how it happened. Okay, so this is the 60s. We're back with Frank Drake here, and where do you look for these radio lines? And Cocconi and Morrison, Phil Morrison from just down the street there at MIT, looked into this. He was at Cornell at the time. Where should you look? Well, you look at the whole radio frequency spectrum, and electromagnetic radiation really is the way to go, sort of by elimination of everything else we know about. And there's this one line, this 21 centimeter line, the thing that was discovered by Purcell and Ewan, and it's kind of the marker out there. It's really the place you look. So these guys suggested that's where you should look. It also happens to be in a pretty quiet region of the radio noise spectrum. Here's roughly what sky noise looks like viewed from down on Earth. So you get these atmospheric lines. The galaxy itself makes a lot of noise. And here's this quiet region in the gigahertz, in the microwave, centimetric microwave. So that's where people look. And now let me show you a few experiments. In the 29 minutes and 40 seconds, 39 seconds, 38 seconds, remaining. I had a sabbatical in '78 and went down to Arecibo. Actually, I wrote a note a letter. Remember those days? To Frank Drake saying I was interested in looking for life in Puerto Rico. He got the joke, and he sent me down there. And I built this little system here that involved, well, actually, Arecibo has all kinds of receiver things, and all you have to do is plug them together. So I did real-time digitizing of what's coming in off the antenna, and recorded this all on a tape, which then got done FFTs offline. Computer wasn't fast enough to do 64K FFTs in real time at a kilosample per second. Can you remember those days? I mean, nowadays your smartphone will do mega channel FFTs in real time of anything you like. Anyway, and here's this Harris computer. I remember this. It was a curious computer, a 24-bit Word. Isn't that weird? And it had a disk drive, which was the size of kind of a small refrigerator, and you stuck these things in. Do you remember those top loading? And it held 20 megabytes. Megabytes, not gigabytes, and definitely not terabytes. And and I remember one day going back and forth on the Pulsar, which was the name of our bus that drove us to this place, calculating what you could do with 20 megabytes. You could put most of the text of the libraries, all the books in the Library of Congress, onto one of those giant 20 megabyte multi-disk things. That was exciting days. Okay, and here's how you built a receiver in those days. That's me, actually. You put your hard hat on. That's mostly for the picture. But you basically built a receiver. It had racks full of things like mixers and attenuators and power level meters. You can see those 2 meters and A to D converters. And you plug them together with BNC cables. You sling a bunch of them over your neck, and you just plug them in, and you do it real quick because your telescope time is coming up. So I did a search down there. I actually looked at 250 stars. It was actually the most sensitive search ever done, and kept that record for about 20 years. It was also a very narrow search. It only looked at about 1 kilohertz, centered on the hydrogen line, and corrected for the Earth's motion around the sun, assuming that the folks out there sending to us don't know what the Earth's doing, but they know what the sun's doing. And it exploited a very cute little way to get rid of interference, which is that because the Earth's turning, the Earth does turn, the Doppler shift along any line of sight is changing with time, and that means that a frequency received from an external fixed frequency oscillator appears to be changing with time. It's a changing Doppler shift. And it changes to the tune of about, at the hydrogen line frequency, it's about 0.15 hertz per second. It's actually always going down. From the time a source rises until it sets, the frequency is always dropping, and when it's overhead, that's the rate at which it's dropping. So what I was doing is 60-second integrations, which gave me a resolution of 0.015 hertz, you know how Fourier works. And, but a fixed frequency signal during that time would chirp about 10 hertz. So it actually would chirp over about 600 channels. So unless you adjust your receiving frequency to compensate for the acceleration due to on the Earth's surface, a signal from space will seem to be chirping, and everything on Earth, all the interference will be fixed and make a big mountain, a big forest of interference. But what you do is you chirp your receiver. It's in here somewhere. Something's chirping. Does it show some chirping? Yeah, here. See, we're programming this first LO. Oh, also this guy. You compensate for that, and the only thing that'll look like a fixed frequency is stuff coming from space. So that was a cute technique. It really worked. We didn't see anything. That's the example of a great search here. You don't see anything. Well, anyway, what happened after this search? I took the stuff I built for there and converted it into what I called Suitcase SETI. This was a little portable apparatus. I'll show you what it looks like. It basically looked like this. This is, again, sort of 1980s technology. Here's a dual Fourier processor. Look at that. It's a whole rack. And it's got a couple of 68,000s cranking away doing 128K FFTs. And here's a machine actually running Unix. In 1980, that was pretty hot stuff, a portable computer. It was made by a company called YCAT that you've never heard of. That's the World Institute for Computer-Aided Teaching. You remember? How do you know about YCAT? Did you work? Yeah. So they had this machine. It only cost a few $1,000s, you know, and it had a 60. It was great. And here's a little video cassette recorder. We put all our data on that. Anyway, here's the box that did the Fourier transform. It's got a bunch of 16K memory chips here. It's all wire wrapped on the back. Here's your 68,000 here. Here's a 16 by 16 multiplier. These things cost a few $100s back then. This is expensive stuff. Okay. Anyway, so Suitcase SETI went down to Arecibo, and we looked at some other frequencies with that. But then, done with Arecibo, came back to Harvard, and we discovered there's this dish out there. This is in Harvard, Massachusetts, on a hillside, or was. You can see it's kind of pretty out there. And so what we did was we got some money from the Planetary Society and built a thing called Sentinel. And we just took this 84-foot dish and built a bunch of RF electronics and made it look like Arecibo to us. We had to build our own local oscillators and all that. And here it is. And we built the system called Sentinel and looked, again, at pretty narrow frequencies. Again, we didn't find anything. It has this wonderful interference rejection. It rejects everything. You never find anything. So then what do? You build a bigger system. So we decided that we needed more bandwidth. We really want to be able to see not just signals that are corrected for our heliocenter, for the sun, but also for other frames of reference, like the galactic center, or the local standard of rest, or the cosmic background standard of rest. So we built a system called META. META stands for Mega Channel Extraterrestrial Assay, and it had 8.4 million channels. And this was amazing for when was this? About 1985. It was really impressive. There's our META processor. It had 128 68,000s with a pile of memory on each one, and lots of block diagrammy looking things. Here's a picture of the control room. It's got 2 racks here full of stuff, and you can't read that, which is good, because it would be embarrassing if you knew that it said Meta Supercomputer, 75 million instructions per second, which was, you know, the Cray 1 wasn't much faster than that. This was a supercomputer. This had 7,000 64K DRAM chips. I soldered them all in, I know. And they cost $3 a piece. We spent $21,000 to get 60 megabytes of memory. You can't imagine yourself in this. It was really like that. Anyway, so some more pictures. Here's a rack full of these. It had 9 of these racks. Each one of those has the memory on it. You can see that. And then it produced this stuff. This is, again, on the YCAT screen. And it gave you the whole spectrum, and then it sort of zoomed in on the largest thing, and then it zoomed in some more. So you could see it at single-channel resolution here. And if it found something big like this, then it put something up on the screen. And a colleague of mine, Bill Press, said, "What's it going to say?" And I said, "Oh, it'll say, you know, big peak, 8 sigma." And he said, "No. He said, "There's going to be journalists there. Have it say something impressive." I said, "Like what?" "Have it say, notify operator immediately. Possible signal of extraterrestrial origin." So there's Bill Press of the numerical recipes fame, you know, right? Okay. This is what you could do back then. It was hard work, but we did it. We didn't find anything there either. Again, we have that same interference rejection. I want to show you just something about the times. So, you know, you think all this stuff seems so primitive, you can't believe that it was hard to do. But let me just show you how hard things were to do. Anybody recognize what this is? No? This is an 8K memory board. This probably cost about $8K. And it has 16-bit words, so I guess you call it 16 kilobytes. And so it's got, I don't know, what, 100,000 cores? Individual cores, these black squares are actually just a mat of little itty-bitty sticky magnetic cores with 3 wires going through each one, an XY wire and a readout thing. And this is for a DEC computer, recognize that kind of thing. And these things cost lots of money, and this is 8K. So the idea of a megabyte, the reason those machines had 16-bit addresses, nobody could afford more than 16 bits worth of memory. 64K, my God, you'd have to be rich. Do you remember these things? Yeah, this is 7-track. I bet you don't remember those. This is, yeah. You could see the bits on this. You put it in Magna-C, and you just look at it with a magnifying glass. You can see the bits. How about this? Yeah. Well, does anybody know the capacity? What is it, like 100K?
Yeah, it's about between 100 and 150K.
Yeah, this one says single-sided, double density. This might be 200K. Yeah. 8-inch floppy. And they were, you see where the word floppy came from. Floppy. Okay, wait. I got a couple of other toys in here. Wait, this one I'm gonna just a sec. Don't look. I gotta give you the quiz here. Okay, there we go. Anybody recognize this?
Oh yeah. It's for printing out a punch card.
Someone told me the other day that there was the analog of this that was for punching, but this was for
Printing the pattern on a card.
Okay, well, yeah. I guess you could. That was a thing you could do. This was a programming drum for an IBM key punch, the 026, 029. And what you did was, you show this to somebody and they say, oh, look, it's got a little set of contacts and it's got a cam here. So it's some sort of mechanic, electro, blah, blah, blah. Nah, it's got these little prongs so that you can stick this thing in and get the ends in without sticking. And then you turn this thing a half-quarter turn, and then you go around like that. Whoops, I did backward. See? And this thing told it to skip the first 8 columns if you hit the tab, because that's where you go to column 8, right? Unless you do a continuation. Do you remember this stuff? Remember Fortran? 6, 7? Yeah, okay. And then after 72 was comments, right? Okay, yeah. This one says dupe 1 to 50, 78 to 80. So this was for, okay, what you say. Why isn't this staying in? I obviously don't know how to use this anymore. I grew up in an 026. I should know. Okay, anyway, I got one last thing. It's older. You won't know this one. Wait, I got 2 things. How about this? Yeah, what's this whole thing? It's an op amp. This is the first kind of commercial op amp from Philbrick. It had a couple 12AU7s. Cool thing. 4 transistors, if you want to think of it that way. Can you build an op amp with 4 transistors? Those guys were smart. Here, how about this? See, it turns. It's got double cotton-covered copper wire on the inside, and if you look carefully, there's a winding inside the outer one. Somebody with very steady hands. And it's got a shaft, and it's got 2 terminals only. There they are. Yes, God, you got some old timers here. This thing appeared in the Sears Roebuck catalogs in the 20s and 30s. You wanted to build a radio. You wanted to tune it. You had to tune each RF stage. And they didn't like variable capacitors. You had to get all those plates to fit in between each other. And they didn't make coils, Bakelite, great stuff. Okay, good. Okay, you guys pass as a group. Individual report cards will come out later. All right, let's see. We went on. Let's see. What did we do? Let me just show you some results from this meta thing. We get a lot of events like this. These are chirped in the chirped frame. Therefore, they're not real. And here's 3 examples of things that didn't do the right thing. But we came up with a few events that we couldn't get rid of. The rejection wasn't complete. And this is a little paper I wrote with Carl Sagan. And you see here that we found 37 candidate events that exceeded the threshold. Here's what they look like on the sky. They're sort of all over the place. A slight, maybe a little bit of preference for the galactic plane, but not much. I think the best thing that came out of this is the food chain of SETI stuff. There's a company that decided to name itself 37 Signals. Here's their logo. And they got it from our search. I don't know what they do. It has nothing to do with SETI. All right, then we decided 8 million channels. That's not nearly enough. We're not finding anything interesting. We need more channels. So we built a thing called Beta, which is supposed to be billion channel extraterrestrial. I say we got only 250 million. That was a lot of work in those days again. And the idea here was, let's get rid of these single events that we can't pin down. We're going to have a 2-beam telescope. And because the telescope is fixed, an east and a west beam, a source will transit through them. So we should see it appear first in the east and then in the west. And just to make sure to make it more robust against local interference, we'll have a horizon-sensitive antenna at the top of a tower, and that'll be the VITO. That's terrestrial. So we built this thing, and here's our block diagram. You don't really care about that, do you? Here's the control room. You can tell something's a little fake because I'm just looking at the greeting screen of whatever we were running then. It must have been Unix, Linux, I don't know, something. So here's our rack. We're down to one rack now, and we actually have lots of bytes. And here's a whole bunch of Pentium, 90 megahertz Pentium PCs. That was state of the art back then, and we cobbled these things all together. Here's what one rack looks like. So it's now the billion-channel extraterrestrial assay. It no longer brags about being a supercomputer. We learned our lesson from that one. OK, so that's what we did. And this thing was able to search the full water hole. That is that whole region from hydrogen to hydroxyl radiation. And the best we got out of this was a few occasional things that never repeated. And we got sort of tired of this, so we said, let's do optical. Whoops. Oh, yeah, we were sort of proud of how fast this thing produces data. 2 seconds of data would fill up a CD, which was state-of-the-art optical storage in those days. And it's also the world's biggest garbage can because we threw this all out except for the occasional stuff that we didn't. So that was cool. That was cool. I'll show you something that's an even bigger garbage can coming up. OK, so we decided to get into the optical business. And you'll remember that calculation. Optical works. And we had this ancient telescope. Look at this thing. Is that cool? Isn't that? Look at this. They don't build them like that anymore. And what we did was we tacked this little box that you see here onto the bottom of this thing and took half of the light out that other people were using for their experiments. And they were looking at solar-type stars for various reasons. And so we just decided we'd take some of the signal and look for bright flashes. Here's a picture of the little box we built. It's made out of half-inch thick aluminum walls because we decided that's the easiest way to tap directly into it. So it ended out it weighed about 100 pounds. There's probably a better way to screw things together. You don't have to make them half-inch thick, but we're kind of, all right. Here's a schematic. We do electronics in this business. This is sort of the front end of this thing. We used what are called hybrid avalanche photodetectors and a whole bunch of other crazy stuff here. Then we decided in order to make this more robust to set up a collaboration with Princeton. So here's our telescope. And at Princeton, they had a 36-inch telescope on campus. And Dave Wilkinson basically arranged for them to build an identical copy of our system on a somewhat smaller telescope and to do simultaneous observations. And the nice thing about that is that when you do simultaneous observations, you're rather insensitive to any local events that could produce a flashing light at 250 miles apart, 300 miles apart, it says here. And even better than that, because that's about 1.6 light milliseconds apart, if you're pointing some direction in the sky, you should get your flash of light at a different time. You know exactly when you should get it. And we did timing with GPS, so we could actually check to see not only if anything ever happened at the same time, but whether it even had the correct delay. And the result of this was that we got basically no further events. Here's some pictures of their telescope getting this stuff on it. We had something like a few hundred single events before we started teaming up with Princeton, but once we did, it drove the coincident event rate to 0. So here's some results. What about all this? If you don't find anything, does it mean anything? Well, it means that the sky's not completely full of people, flashy things, men in black, flashy thing. But the limits are kind of weak. You can set limits of the fraction of stars that have transmitting civilizations that happen to be transmitting at us with a nice bright thing at the time we were looking. So that's the kind of numbers you get. I'll show you a better slide on this when we got to a bigger experiment, which is the next one, which is we decided we need to not just look at star by star, but the whole sky. And this came out of a challenge. I was on a committee thinking about how to do SETI for the next 20 years, and there was an optical astronomer there, a rather famous one, who said, of course, optical, you can't do all sky because you're using telescopes. They only look at one thing. I thought that was a really cool challenge. So I came back and said, let's build an all-sky optical SETI. So here's how you do it. You get one of these things, and you start knocking down trees and building, and you dig ditches, and you find that there's wires in there, and then it snows, and you pour a foundation, and then the foundation, you get this kind of thing. This is where the telescope's going to go. And then you start putting a roof. You make this thing out of steel, and you put a roof on it, and there it is. Look at that. It's got a roof, and it goes on rails. It's a roll-off observatory. Here comes the telescope. It was made in Arkansas by some guys who didn't need much money. They gave us a 72-inch, 6-foot optical primary, a 3-foot secondary, the mount and the drive system and everything for $50,000. Real bargain. So we got this thing, and here it is with our telescope, the roof rolled off. Here's a couple of the graduate students who are working on this. And there you can see this telescope pointing up into the sky. This is out at Harvard. And this thing is still working now. Ran it just the other night. Here's some pictures. This is what it looks like from the inside. Here's the control room. This time we're actually running Linux. This is for real. And Andrew, the student in that picture, designed a chip to do optical coincidence and amplification and all that. And here's a bunch of these boards with these chips and a whole pile of fans inside this box that hangs on the telescope. Here's some fat wire, because we're running about 80 amps at 3 volts to this thing. Here's the motherboard and a daughter board and a detector and a pencil. The people don't use these anymore, except, hey, is there a thing called Apple Pencil? What's that thing? You remember if a stylus shows that you failed, but then there is one, but it's not called a stylus? You know about that? No? Yeah? OK, whatever. Anyway, here, this is a real pencil. This is, OK. Oh, yeah, hey, so I stole this slide from my student, and you see, look at that. I don't know how to do that. Anyway, here's his chip. Chip took him 4 years to get it to work right. It was a lot of work. And this thing basically lets you look at about a gigasample per second of data coming in on a big panel of stuff. Look, here's us building these things and bringing it out the door and over to the telescope. And here we are inaugurating the observatory. And here's first light, first night. So this guy went from senior at Harvard to Google. You guys swallowed him whole. This guy went to Apple. And this guy went to Harvard. This guy, by way of the South Pole for a year, went to Harvey Mudd College. So there's life after SETI, though it may not be SETI. And here we are, basically getting all this stuff working. It's a really nice interface. You have these little things you click on, and a whole panel opens. It shows you what the observatory is doing. It shows you what the power is doing. It has a few webcams, and it shows you pulsed-like optical events down here. See what's coming up here. Oh, it says show time-lapse skycam movie. All right. This is what the sky looks like just out in the countryside here at Harvard. You don't see this from Cambridge. You know, people who live in cities don't know that there are stars. And those little flashes, those are airplanes go through. These are 10-second exposures taken every few minutes, so you just get little flashes of that. Probably occasional satellite in there. You may recognize a constellation. And then you'll recognize moonrise, because it completely clobbers the sky. Here, I think that's what's happening there, something very bright. That's not the moon. That's light reflecting off this tree that's over here. Anyway, here comes the moon. OK, wham. OK, wow, OK. And now I think in one here you see the roof opening, one of these things. Let's see. Look at that. That was a roof. Wow, look at that. OK, anyway, that's kind of cool, huh? All right. Well, there's some clouds. We get that, too, here. Look at that. Is that great? I'll show you the kind of events we see with this thing. So we're looking for short pulses of the kind that the calculations showed that you could project across these distances and outshine your star. And here's the kind of thing we occasionally get. This is an interesting event. And here's what it looks like on these detectors. I didn't describe this, and I won't really, except to say that we have these detectors that are 8x8 arrays of photomultiplier tube photocathodes. And they're arrayed with a beam splitter, so they form a coincident pair. And we insist on a coincidence. That is, something hits the right panel, has to hit in the corresponding place on the left panel. And here's such an event that occurred back in 2007 and tickled these two detectors. And the red and blue traces here show the right and left signals coming out of these detectors. So this is the kind of thing that we've been looking for. And here's the kind of sensitivity it sets for fraction of stars with transmitting civilizations. You can see it's really quite a bit better than, here's when we covered more of the sky, than when we had the targeted search that I showed you earlier with that ancient-looking telescope. And the reason is we're just covering a lot more sky. We're covering it for less time, so it's less sensitive to transmitters that don't repeat very often, because we only spend about 1 minute on any given place in the sky. And here's some sort of a little bit of interpretation about the context in which that makes sense. Now, I'm going to accelerate a little bit here, because there's some cool stuff coming up. The last thing we did with this experiment is this student, Curtis, who wound up now at Amazon. I'm sorry, he wound up at Apple. Those A companies, you know. And this is the thing he built. He came up with a really clever idea, which is this. If you take a fancy FPGA, one of these Xilinx parts, they have a whole bunch of inputs which are meant for digital signals. They're LVDS differential pairs. But they're very good comparators. So you can trick it into being a flash analog to digital converter, even though it doesn't know that's what you're doing. So you tie 8 of these with a common signal input and a progression of biases, and you've got yourself an ADC. And you can run these things at 1.5 gigasamples per second. And you can put 32 of these into one chip. So he's got 2 pairs for the left and right matching pixels, and then he's got 16 of those things in one of these chips. And it's got all kinds of other junk in here. You know, these chips are full of stuff. And in fact, here's this whole little thing with this front end. It's also got, heck, you can drop a microblaze into there, and you've got an Ethernet MAC into this thing, and you know, you name it, it's got it. So he's actually got, each one of these things is a node on our network. And he put these things together, and the damn thing works. Here's an example of a double pulse feeding into this thing. Notice we use nonlinear levels, because you can do that if you set your own trip points. And the jiggly red line is ground truth with a gigahertz scope, and the black line is what this crazy kludged up ADC measures for a double pulse. So it works great. The thing really works. So we've had this thing looking at the sky, and we see events like this. This is a cool event, because look at this. It's matching left and right, and it's a short pulse, even when expanded here. Here's something that it's something a little fishy about it. It hit an awful lot of pixels here, and look how long the thing took to spread out like that. It's really greatly expanded in time. It's actually taking a significant fraction of a microsecond. Guess what that is? It's an airplane, because our Skycam caught it in the act. Here it is flying toward our thing, and then it went through, and we saw this gigantic thing. So we see some of those things from time. Now it says show. OK, so here's what, and here's another kind of event. This is a cosmic ray, which hits a whole bunch of pixels like that, but also is short pulse, and we're sensitive to these things. I'm going to skip the movie and just show you. This is the amount of the sky that we've covered now. If it's brighter red like that, it means we've covered it multiple times. So we've covered basically the whole sky multiple times with this search. Here's an example of another event. You know, here's again the sky, and here's these little pulses. And we see these things from time to time. They've never repeated. The telescope automatically goes back to that declination and tries to do it again the next night. So this is some of our non-events. Now here's an example of a real event. We have another camera at the observatory, and it looks at our observatory. It looks from the central building. We get these kind of creatures, not exactly extraterrestrial, some degree of intelligence, though. What we did is we decided, in order to eliminate isolated events, we needed 2 sites. So here's Curtis at the Mount Hopkins Observatory in Arizona, with this big telescope used for cosmic rays. Cosmic rays generate light flashes when they come through the atmosphere. And what he did was, there's what its detector looks like. He rigged it up so we were running both experiments, since ours runs remotely. Here's the Massachusetts, our observatory, and here's Arizona. And here's Curtis looking for simultaneous events. And that drives the data rate all the way down to 0. Well, here's where we are now with this experiment. This is actually just a few nights ago. This is January 6th. And we're still running this thing on every clear night. People always want to know what you found. It's kind of, you know, it's sort of sad. We find occasional events. This is WOW signal from Ohio State in the 60s. Here's this kind of thing with the notify operator immediately, occasional events. Here's the optical SETI, and we get these occasional events. What we need really is more observatories, greater sensitivity, immediate follow-up. So let me just tell you in the last 1 minute and 50 seconds what's happening. There's this new initiative called the Breakthrough Listen. It's funded by a Russian billionaire. He pledged $100 million. And what they've done is bought telescope time, at least for the first few years, on 3 of the best telescopes. This is the Green Bank steerable 100-meter dish, biggest dish in the world, steerable dish. Very good system temperature. It's got an offset Gregorian feed. It's a really classy piece of stuff. This is the Parkes telescope in Australia, which gets you the southern sky. And this is the automated planet finder at Lick, which has a very high resolution spectrometer used for planet finding, but it's also a terrific telescope if you want to look for little laser lines in the middle of the thicket of lines that come from a star. So these have all been pressed into service. Here's some of the technology. Let's see, I want to get to the target. Here's the technology. The guys at Berkeley who've designed some really fast stuff have these FPGA-based boards that can do 26 gigasample sampling. They generate 320 gigabits per second of data. They're doing 10 gigachannel spectroscopy on a 10 gigahertz bandwidth. Really incredibly nice stuff. And here's the stuff they're going to look at. Some targets. Produce a lot of data. Look where it winds up. In your cloud. You are here. Here's one of their boards that's a 26 gigasample per second thing. And here's one of their block diagrams. These guys are very good at this, and this Casper project has built beautiful FPGA-based hardware that's used for all kinds of things, not just astronomy, radio astronomy. It's used for protein folding stuff and MRI and all that kind of stuff. Future, a couple of things going up. There's some arrays going up. 4 seconds, 3 seconds. This is in China. This is going to be the world's biggest telescope, 500 meters. I think it's now finished. Here's an array that's coming up. And here's a piece of the SKA, the square kilometer array in South Africa. It's called Meerkat, which is an acronym for something. But that's also that funny looking animal kind of look like this. You've seen those things? Interesting question, what you do with arrays. Arrays are very good because they discriminate against things in different directions. They also can produce multiple beams at the same time with full sensitivity. So they're nice things. This is actually my last slide, 0 seconds. Let me just show you here. This is an interesting thing, which you can put a bunch of antennas up. Do you make them big or small? If you make them small and you want a lot of aperture, you need more of them. So you spend more. They're smaller dishes, cheaper, but you need more of them. You have to connect them together. This is sort of showing you the partitioning of costs in euros of telescopes as a function of dish diameter. So a few big ones, a lot of little ones. Building a lot of little ones is cheaper on the dishes, but you got to need more wiring, and you need a lot more electronics in the car later and in computing. This figure of merit here is a figure of merit that has to do with degrees of sky covered times area of collecting area divided by system temperature. It's sort of the right figure of merit for this kind of thing. And what you see is you actually get a much better figure of merit with small dishes. And the reason is that each dish, because it's small, covers a lot of the sky. And anywhere within that sky, you can form beams using all of the dishes. So you cover a large piece of the sky with as many as n or n squared beams simultaneously with a lot of small dishes, whereas with big dishes, you can only look at a small piece of the sky. So it actually pays to do that. Right now, it costs kind of a lot. On the other hand, this is the stuff that gets cheaper, the computing and the correlating. And so really what you should do is you should bias towards the left side of this bar graph and build a lot of small dishes. And that's where people are going with this. Anyway, I would say, in spite of all these rather stupendous efforts, we're still in that last tenth of a millisecond of Earth's attempt to do this right. We're still the small fishermen in this business. And for it to succeed at this point, we'd have to be extraordinarily lucky. That's my story. Thank you. Did I leave you questionless? Impossible.
So I'm wondering, I mean, this sort of assumes that somebody out there has identified us as a potentially interesting candidate, and they're sending a pulse directed at us to see if we're listening. But I'm also, what would we look like to a civilization, you know, 1,000 light years away? Like we're sending out a bunch of RF stuff. Is it sort of theoretically possible for somebody to look at what a civilization that just started emitting RF signals would look like?
Yeah, good question. So the question is, could we detect ourselves with these kind of experiments? The answer is no. Not maybe from the nearest star, but unlikely, because the radio signals we're creating are not intended to establish communication. They're either piped through pipes, or they're radars, and they're just briefly pointed in any given direction. If they're radars, they're broadband. If they're FM broadcasts, you know, they're aimed horizontally. We're doing it all wrong, but we're not looking. Maybe a sufficiently advanced civilization could do huge antennas and find us in our primitive stage. We're looking for intentional beacons. And the idea of those first couple of slides is if we wanted to make an intentional beacon, even with our technology, we could do it now. But we're certainly looking for something optimized in that way. And once it's optimized in that way, it becomes detectable even with our technology. But we could not detect twin if they don't go to the effort of doing that. Some of these targets in that breakthrough are interested in when two planets are aligned around some other star, might you pick up, by chance, a communication that's between their two planets? You know, if you look at the piece of phase space that occupies, the answer is, what are you smoking? It's just too improbable.
So are there any efforts or discussion about doing things like picking star systems with exoplanets and
Yeah, if you go
China
back to
lasers,
the,
that
so somewhere here I had the targets. I zipped through at warp speed, so you probably, here's what they look at. Nearby stars, why not? You know, nice strong signal. Sunlight stars, yeah, because we think that, we know you can live around a sun-like star, at least for a while. Known exoplanets, sure, but you know, that's a pretty small fraction. After Kepler only picks up planets that are in our plane, so it misses a lot of them. Here's this alignment thing. I think this is nutcase SETI, but there it is on the list, and a few other ideas. But basically, and the galactic plane, because there's more demography there. And I think also not on this list are other nearby galaxies. You know, you point your beam at Andromeda, and you pick up 10 to the 11th stars in one shot. And you might say, oh, but that's 2 million light years away. You're not going to. It's a weak signal. Well, think again. If Andromeda is trying to illuminate our galaxy, they'll make a beam that just covers our galaxy, arrives with the same strength as a signal of someone within our galaxy also trying to illuminate the whole galaxy. So it really doesn't matter how far away you are if you tailor your beam to match the target size. So I think that's a perfectly reasonable thing to do. Did that answer the question?
Sure, thanks.
Over there.
Possibly sort of related. I totally buy the concept that we're really early on the technology side in the cosmic scale of time. But that's still going to be true in 50 years. That's still going to be true in 500 years. What if everybody feels that way? What if they're all just listening, waiting for the other guy to do the hard part of sending signals?
Yeah. Well, I hate that question. So I guess I'd say, ask me again in 500 years. You know, there comes a time at which you think you've done a fairly thorough scouring of receiving, given the distances and what you know about planets. You know, we're learning an awful lot about these planets, and I think we're gonna have much smarter searches in a while. You'll always be able to make an argument like that. Maybe ultimately we'll just decide we're the only ones there. I find that a completely
Well, I'm wondering if
implausible
there's any sense of a technology that you might expect to hit at some point where you go, oh, wow, we can send signals now.
Some people argue we should be symmetric right now. I mean, that we only earn the right to listen if we transmit. And I'd say we'd be nuts. We'd be so embarrassed with what we sent if we do it now, because we're so primitive. And the other thing, so let me just toss this idea out. When we first make contact, it's not going to be the first time it's ever happened. That would be astonishing. It's happened lots of times. And in fact, if there's sufficiently high density of such civilizations, then they sort of have a network. They have a galactic internet. They've fashioned the ideal acquisition signal. They've done this a million times. It comes with the whole mess. You know, it's like the movie Contact. They know what they're doing. And we just go shouting in there with a bunch of garbage and noise like mumblings, and tell them about the wars we're fighting, and, you know, is Donald Trump going to be the president? And they were just going to say, oh, there's no intelligent life on Earth. You know. So no, I think at this point we definitely don't transmit. Although there are people who say that's wrong. There's other people who say we shouldn't transmit because they're going to come and eat us. I think that's kind of extreme, because I think if they can actually come here, then they've grown up enough to know not to go killing stuff off. Again, you can find argument against this, but I guess I can say, you know, in the next few decades, I'm okay, and after that, I don't have to worry about it, because I'm already 73 years old, and the average lifespan is, I'm pushing up against that, right? It's your problem. Are there any other? Here's a question. Yeah.
So if there are really advanced civilizations, like galactic scale civilizations, do you think that looking for pulses of light from these things is the only way to detect such civilization, or might there be other things we would look for?
Yeah, we have to sort of think about what we know now. I mean, we know the electromagnetic communication is cool and can do the job. If the galaxy is really colonized, you might imagine that they might have robotic probes that go in orbit around likely stars, where they have planets, and maybe do some local back and forth. Wouldn't that be a smart thing to do? People have looked for stuff like that, haven't found it. I think if we discover new modalities of communication, they're fair game. But from what we know now, we don't like particles that have mass. They go too slow and take too much energy. We don't like charged particles because they bend in magnetic fields and they scatter. We don't like neutrinos and gravity waves, gravitons, because they're too hard to make and detect, and this is certainly decent physics. Whereas spin 1, mass 0, electromagnetic waves just seem to have all the right characteristics. It works at extremely sensitive level, and they go at the speed of light. That's as fast as you get to go, right? But we're certainly open to other things. And with the galactic, if there is a galactic network, they'll eventually notice us. Maybe to join the club, we need to detect their signal. Maybe they don't like getting in touch with two primitive civilizations, and we are still on we haven't earned our entrance ticket yet. But this is all crazy speculation. The best you can speculate about it, but if you actually want to make something happen, you go look for the signals and do it the best way you can. Yeah.
Hi. So how well can you plausibly aim a laser? Like right now, if we wanted to and NASA would shoot it up into space or whatever we were going to do with it, could we pick a star at 70 light years and say there's an Earth orbit around that and we want to bathe that orbit in light? I mean, could we hit that point in space?
Yeah. Actually, it was part of that nerd box that had a lot of stuff in there. Talked about the size. You'd actually have to broaden it. The calculation I did was for an 1 AU target diameter at what I forget what the distance was. I think it was 1,000 light years, and that's diffraction limited for the 10-meter telescope. If you want to spread it out because you think the planets might be further out, you can do that, and it reduces the flux by the square of the. Yeah. Well, not going through the atmosphere, you can't. So this would have to be an orbital thing. And the question is, can you do fractional arc second? You can do diffraction limited with a 10-meter telescope, and we're going to get better at that. I mean, it's really easy in space. Everything's very quiet. There's no weather, there's no wind. You don't get snow advisories. It's basically, or backside of the moon might be a good place to put telescopes. It's quiet there too, and it shields you from all the interference from Earth. If you want to do that kind of thing. Another one. Yes.
I have a really down-to-earth question. In the edition of your book I have, it's probably the second if the third one is the new one. There's this wonderful-looking technology where you put these sticky wires on a board, and you can prototype your thing without a circuit mill or without chemicals. And that disappeared. And do you know why?
Gee, I remember. I'd forgotten completely about that. This is
Cole-Morgan multi-wire.
Yeah. So what it did was it was basically an alternative to PCBs or wire wrap. And what it did was it just spit it out a sticky insulated wire. They could cross over each other. I remember I got a board for a Nova that was a video board, and it was made by a local company, and they did it with the system. And they went around, when it got to the pad that it was supposed to go to, everything was through-hole in those days. It actually just made a little welded spot. And so the wires could cross with reckless abandon. You didn't need multiple layers or anything else. Why did it disappear? It's probably a crappy way to make more than one board of anything, and the etch boards are much more effective, particularly if you have multi-layer. I don't know. Wire wrap kind of disappeared.
With the pulling from the pads if you flex them.
Is that right?
I heard that somewhere, yeah.
So don't flex them.
Yeah, the board stiffeners.
I mean, who would ever think that surface mount could work at all? You have these little ceramic chips, right? And you're soldering both ends down, and now it's on a board, which, by the way, is and you go like that. Why don't they just all pop off? I mean, don't you get when you shove the heatsink down when you stick the CPU on your motherboard, and then you push that thing down, and it's supposed to snap in, and the board goes like that, and it's all full of these little. Why don't they just go like that and fly into the air? They don't, but it shouldn't work. Jim Williams, linear technology, used to say all the things that shouldn't work. He says, disc brakes can't work. He said, ballpoint pen, I would have fired that guy. So you can make things work. You just have to work hard to make them work.
A theme that sort of recurred throughout the course of your talk was the sort of advances in technology over time. And corresponding with that, there's also a decrease in the cost for any given unit of, say, computing power over time. And something that I thought that was really cool that happened a year or so ago was the IS EE3 reboot project, where a bunch of guys in Mountain View took over McDonald's and then took over a NASA probe and tried to adjust its orbit and so on, and they failed because there was no pressurant in the fuel tank for the thing. But this idea of sort of reclaiming old technology at the individual level, and now I'm kind of wondering what your thoughts are on sort of at the individual level, somebody who's interested in this stuff, going into their basement and building a device with the same computational power of the meta array that you guys have built in the 70s and 80s, and trying to do the sort of same experiments you guys were doing. Is there any merit to that? Does that add scientific value?
Yeah, interesting. This big supernova that was just discovered this week or last week was found with a bunch of automated small telescopes that's run with a sort of small consortium. And there's nothing there that's beyond amateur status. In particular, by amateur, I don't mean I don't mean not smart. I mean doing it for the love, right? That's where the word comes from. You can do an awful lot with computation. And as that graph showed about how you build your big telescopes, the computation is where it's at if you have a bunch of small telescopes, and you can do amazing things. So I think amateur astronomers are definitely in play, particularly when the phase space that you have to explore is the whole sky, and most of these projects are looking through soda straws at particular places. I think there's definite chances. In fact, you might say, why aren't these signals strong, given that even now we could make signals that are quite detectable? We can make, a CW laser at 100 megawatts, diffraction limited, is much brighter than the star. It would be a spectral. A star would turn suddenly green or blue. Why don't we see those things? So probably because they don't need to go that much overboard to bring a new civilization in. But if they're interested in bringing a new civilization in before we blow ourselves up, or elect a really untenable president, then it may pay for them to send pretty strong signals, in which case I think 1-meter class telescopes, or robotic telescopes on which you can derive some stream of data from it, or these data streams can be split and provided to multiple users. I think it's definitely a thing to do. And with the availability of cheap GPUs and FPGAs and boards that do all this stuff, the Adafruit and SparkFuns of the world really make this easy stuff. So I say go for it and report back.
I remember there was a SETI at Home program that would take spare compute cycles and go off and look at signals. Yes. Is that still ongoing?
Yeah. In fact, SETI at Home. So SETI at Home is run out of Berkeley by the same folks who bring you this Casper project and the FPGAs that I showed you. And SETI at Home takes data from the Arecibo telescope. The Arecibo telescope is this dish with the thing sticking down, and because they want to keep pointing at the same thing, the feed has to move, so the thing swivels around and goes in and out. And the other feed isn't doing anything. It's doing curlicue. So SETI at Home took data from the curlicue feed that nobody wanted, and basically parsed it up and sent it all the way out to everybody to run on their things. And there's wonderful maps of the sky as curlicued with SETI at Home. That's alive and well, and in fact, this new project, Breakthrough, is going to make public all of its data in some form that's actually usable. Not the full 320, gigabits per second, but some cleaned up version of that. Part of their mandate is not to sit on this data. The same way Kepler data is made public, and the Public Genome Project, publish their stuff too. So if what you want to do is software on someone else's data, you'll have more than you can handle. And I don't know if that's going to be turned into I see flashing lights. That could be a laser pulse from alien intelligence, or it could be a sign that I'm supposed to stop talking. I think the latter. Thank you.